You've prepped the field, dialed in your nitrogen, and the season starts strong. But then, right when the crop should be taking off, it suddenly hits a wall. Upward growth stalls out, and your forage quality drops. The hidden culprit dragging down your harvest is likely a severe lack of soil sulfur. We are largely victims of our own progress here. Thanks to cleaner air standards, we receive far less sulfur fallout from the atmosphere than we used to. Combine that with high-analysis fertilizers that strip out sulfur impurities, and natural soil reserves are dropping fast. We can correct this. By the end of this video, you'll know how to spot the shortage, feed the invisible microbial engine in your dirt, and pick the exact right fertilizer to get your crops growing again. Solving a sulfur shortage reactivates the plant's internal growth machinery, allowing it to synthesize the nitrogen and water it is already pulling from the soil. Step 1 is identifying your risk factors. If you are working with light, sandy textured soils that are low in organic matter, you are a prime candidate for a sulfur shortage. That organic matter is crucial because it acts as the vault holding most of the natural sulfur in your soil. When it gets stripped away by erosion or over-mineralization, those native reserves go right along with it. In the plant itself, a shortage shows up as failing chloroplast function. The leaves turn pale and yellow, and if you are growing legumes, their ability to fix nitrogen grinds to a halt. When a plant has the nutrition it needs, proper chloroplast function looks like this: lush, deep green foliage and vibrant growth. This diagram shows the chemical structure of methionine. Notice the sulfur atom right in the middle of the chain. Sulfur is a mandatory structural building block for this and other vital amino acids. Without it, the plant's internal protein factory shuts down entirely. You can apply all the nitrogen and phosphorus you want, but without sulfur to complete the chain, the plant cannot synthesize those nutrients into growth. For step 2, we need to clear up a major misconception. Plants cannot eat raw organic or elemental sulfur directly out of the soil. This illustration maps the sulfur cycle. Notice the downward arrows for decomposition. Raw sulfur must be converted into sulfate, or SO4, before it is plant-ready. This process is known as mineralization, and it is driven entirely by an invisible workforce of soil bacteria. Once the microbes finish that conversion, follow the path back up. The roots can finally pull that processed sulfate out of the dirt to fuel the trees and grass above ground. This graphic shows a Gradsky column, mapping a living soil gradient. Pay attention to the oxygen scale on the far left. Different specialized bacteria handle different stages of this chemical conversion, depending entirely on the oxygen levels at their depth. Down in the deep, low-oxygen mud at the bottom, anaerobic sulfate-reducing bacteria are doing the heavy lifting. They use a completely different metabolic equation compared to the purple and green sulfur bacteria operating closer to the surface. Managing soil sulfur means managing this living microbial workforce. If those microbes aren't actively processing, your plants are starving. Step 3 is fixing the deficit. Choosing a fertilizer is a strategic decision that depends entirely on your required timeline and your specific soil pH goals. Option A is gypsum. This delivers immediate, plant-ready sulfate. It is a fast fix that bypasses the microbial waiting period entirely, and it has a neutral impact on your overall soil pH. Option B is elemental sulfur. This is a slow-release option that requires time for soil bacteria to break it down before the roots can absorb it. That microbial process comes with a crucial side effect. As those bacteria oxidize the elemental sulfur, they actively lower the soil pH. This reaction is highly effective for mitigating sodicity, meaning soils plagued by excessively high sodium. But that same pH drop becomes a major liability if your field is already highly acidic. Driving it down further will actively harm your crops. Your sulfur amendment feeds the crop while providing a mechanism to actively steer your soil's chemistry and application timeline. Step 4 is getting it out into the field. You can broadcast it widely from a spreader, band it near the seedbed, or run it straight through your furrow and sprinkler irrigation systems. But application is only half the job. If you selected elemental sulfur, you have to activate it. Because it relies on living bacteria, your soil environment has to be hospitable. These microbes demand adequate soil moisture and consistently warm temperatures to wake up and process the applied material. Simply spreading elemental sulfur over dry, dead dirt yields zero plant-ready sulfate. The physical environment must support the biology. Let's review the steps. You've diagnosed the shortage in the plant, chosen the precise amendment for your soil profile, and activated the microbial workforce. With that system running, the plants finally have the raw materials they need to synthesize proteins, build vitamins, and maximize their photosynthesis. Your final task is simple. Pull a soil test at the end of the season. Monitor your standing sulfate levels and make sure your pH hasn't drifted out of its optimal range. By mastering the sulfur cycle, you stop guessing at nutrient needs and begin engineering a high-yield biological system.